Hello, welcome honors students. I trust you're doing well. Today we are going to go through a virtual lesson going through the actual study guide for chapter 13. So if you happen to look in RenWeb, and hopefully you are paying attention to both RenWeb and Moodle, you may notice that we have our first Moodle test coming up on Monday, and it will be on chapter 13. So this is the study guide for that test. So I want to go through this with you. Same process as we do in class. The only difference is you're gonna probably have to pause the video from time to time in order to fill in your study guide. Now I posted the study guide for you yesterday so that you have the opportunity to have gone through it a little bit, seen what questions are on there, and today we're going to run through it as a virtual lesson. And I'll give you a little bit more information on that test on the next virtual lesson that I do. So here we go. Number one, the energy of motion is called kinetic energy. So when you talk about motion, moving objects, that's kinetic energy. We learned the other type of energy is stored energy, stored in bonds, stored in structure. That's potential energy. But if anything is moving, that is kinetic energy. And all objects have kinetic energy because all objects' particles are moving. We'll talk more about that here in a little bit. So number two, what does the kinetic theory state of all matter? Well, all matter is made of these tiny particles that are in constant motion. The motion depends on what type of matter you're talking about. Is it a solid? Is it a liquid? Or is it a gas? Each one of those, the particle movements are different. But when you talk about the kinetic theory of matter itself, is all matter is composed of tiny particles that are in constant motion. Yes, gas much faster than a solid, but nevertheless, they are still in motion. Number three is the kinetic theory about gas, and this here is, these 3 points there are very important. This is the kinetic theory and the 3 assumptions that are made in particular about gas. Number one, the particles in the gas are considered to be small, hard spheres with insignificant volumes. Think about that for a second. Small, hard spheres, that's the nucleus. So it's talking about the actual atom itself. Remember that they're extremely tiny. When you talk about a single atom, it's insignificant, the volume that it takes up. It takes literally millions of atoms to make up enough to have some volume. So, and we're familiar with that from Avogadro's number, and 1 mole is 22.4 liters. So that's a huge number if you remember that. So number one is particles in a gas are small, hard spheres with insignificant volume. Number two, the motion of the particles are constant, rapid, and random. Gas particles are going all directions. There's little to no attraction at all when you talk about gas particles. There's no attraction to each other. So they're just going all over in constantly random and rapid motion. And the last assumption, number three, all collisions between particles in a gas are perfectly elastic. That means you have a particle coming across, striking another particle right here, and it bouncing off. The energy that it struck with, it's going to leave with. It's just striking and leaving, striking and leaving. So there is no loss in energy. So that's what perfectly elastic means. So all collisions between particles in a gas are perfectly elastic. No energy loss. So those are 3 assumptions of the kinetic theory, in particular about a gas. Now the next chapter we're going to go into, chapter 14, is all about gas laws. And there's several gas laws, and we're going to work through them, and you'll have a much better understanding of these 3 assumptions once we complete that particular chapter. Number 4, gas pressure. What is gas pressure? So we talked about all this motion, all these gas particles are striking and bouncing back. So if you talk about putting some gas in a container, that gas is going to be flying around, striking the walls of that container, and it's going to apply a force. So that's gas pressure. The result from the force is exerted by a gas per unit area of an object. The collisions of moving particles exert force when it strikes an object. Think about a balloon. You blow a balloon up, inside there, why is it inflating? It's overcoming the atmospheric pressure that's around it because more and more volume of gas is going inside, and those particles are striking the sides, and that's what makes it inflate. Number 5, a vacuum. A vacuum is an empty space that has no particles, and therefore, if there's no particles, there is no pressure. Space, outer space is a vacuum. That's why astronauts have to wear that full suit. There is no air, there's no gases. So therefore, if there's no particles moving around and striking anything, there's no pressure. So that's a vacuum, an empty space with no particles and no pressure. Number 6, atmospheric pressure. When you think about the Earth's atmosphere, we have gravity, 9.8 meters per second squared. So when you talk about it's pulled in and kept in our atmosphere here on Earth, well, all this gas that we have all around us, there's oxygen, there's nitrogen, there's hydrogen, there's carbon dioxide, there's helium, there's different gases that are all around us. They're moving and they're striking. That is atmospheric pressure. So the collisions of atoms and molecules in the air within Earth's atmosphere results in atmospheric pressure. So you're on sea level, your atmospheric pressure is going to be much higher here than if you went to the top of a high mountain. Now the air is thinner, which means less particles. So now you have a lower atmospheric pressure. Number 7, a barometer. A barometer is a device that is used to measure atmospheric pressure. Now, they're not that common anymore. You've probably seen barometers in your grandparents' home, but nevertheless, they measure atmospheric pressure. And how does it do that? It was measured in inches of mercury and millimeters of mercury, because what they have is this tube, something like that they have in a container, and that container is full of mercury, and the atmospheric pressure is forcing down on it like this. And what happens is before they put this tube into this vat of mercury, they fill it completely to the end, and then they tip it and put it right down inside. So that mercury creates a vacuum at the very end right here, and then they measure that. And that's where you get millimeters of mercury. And so when you talk about this full distance, the atmospheric pressure forcing down, these arrows that you see coming down, is going to force up the mercury. So they have the total distance of this tube. Then they have the gap at the top here that'll be a vacuum, and the measurement from here to the bottom is in millimeters of mercury, and that's the pressure. So the less pressure, the less force would be pushing down. So you have less millimeters of mercury, so less atmospheric pressure. So that's a simple device that is used, and it is a barometer. Number 8, the SI unit of measurement for pressure is Pascal. That's really important, ladies and gentlemen. Please make sure you write that down. It's not kilopascals. It's not atmospheres. It's pascals. The units that we will use in dealing with gas pressure isn't pascals. It's kilopascals and atmospheres. Those are the two most common ones. So the conversions, you have a worksheet coming up due tomorrow. And that is the conversion. So I'll make notes on that. Hopefully you watched one virtual lesson I placed on Moodle for you, where I broke down various conversions. So it's pretty important. This conversion is 1 atmosphere equals 760 millimeters of mercury equals 101.3 kilopascals equals 760 torr. Real important numbers that you do need to get those to memory. So check Moodle for the corrections, and that's what I have written right here. So I'll make notations on your worksheet. Number 10, how does kinetic energy relate to temperature? Think about what temperature is. Temperature is the measurement of the average kinetic energy. Specifically, we're talking about Kelvin. Well, you can convert Kelvins to Celsius, but the Kelvin temperature is the average kinetic energy of a substance. So when you take the thermometer and you take the temperature, you are actually taking the average kinetic energy. So remember, it's an average. And an average is, and we talked about this previously, a bell-shaped curve. So you have, if your average is right here, you have some lower and some particles higher if that's your average. So please keep that in mind. Temperature is the average kinetic energy. Number 11, let me slide this sheet up just a little bit more. What is absolute zero? Please remember, it is theoretical. It's never been achieved. It's come very close, but it is the theoretical temperature in which all motion ceases. It stops. Particles stop moving. So it is 0 Kelvin. Kelvin never has a negative number. So it is negative 273.15 degrees Celsius. Number 12. Here's a little differentiation chart. You guys know I like differentiation charts. So here we have our gas, liquid, solid. So molecular motion. Gas is rapid and random. Liquid is flowing. It's moving past one another, rotating around. It's not flying far away from each other because there is attraction. That's why it's a liquid and not a gas. And solids, they're rigid. They're in a fixed position, just vibrating in a fixed position. Fluidity. Gas is fluid, which means flows, which means a molecule can move past one another. That's what flow means. It can move past one another. So when you see fluid, that means it can move past one another. So gas, yes. Liquids, yes. Solids, no. That's why it's a solid. They're a strong attraction, which makes it rigid. Compactability. Gas is very compactable. There's a lot of space in between it, and you can compact gas. Liquids, you can't. That is why oil is used in hydraulics, and you see them in loaders and backhoes and those construction equipment that uses hydraulics, which uses an oil because it's not compressible. And solids are not compressible. And these are all in the normal means. If you put a solid object in a crusher, it'll crush it, but that's not normal means. Density. So density is the mass per unit volume, if you remember that formula. So when you talk about a gas, it's very low. The density is very low. Liquids are moderate. Solids are very dense. Next, we have particle attraction. A gas has little to no particle attraction. Liquids, there is attraction, particle attraction in a liquid. Solids, strong attraction in a solid. That's why it's a solid. The difference between a solid is attraction is so strong it becomes rigid. A liquid, there's attraction, but it can move past. The molecules and particles can move past one another. So that's why it can flow. The shape. Gas has no shape. Liquid has no shape. Solids have a definite shape. Volume. A gas has no specific volume. It will fill whatever size container it's placed in. However, a liquid does have a specific volume. It's real important to remember that. A liquid has a specific volume, and a solid also has a specific volume. So this differentiation chart right here, pretty important. Let's move down a little bit further. What is meant by fluid? You heard me mention this just a little while ago. The molecules can move past one another. That's called flow, fluidity. So gas and liquids have the ability to flow. Solids do not. Number 14, vaporization and evaporation. Two different concepts. So let's make sure we got that. So the definition of vaporization, the conversion of a liquid to a gas. A vapor is the gaseous form of a substance that is typically a liquid at room temperature. So that's vaporization. Evaporation is the conversion into gas on the surface of a non-boiling liquid. That's evaporation. That's the water. If you spilled a cup of water, come back in an hour or so, a lot of the water's gone. That's because it evaporated. It's not boiling, but some of the surface molecules will overcome attraction and atmospheric pressure and escape as evaporation. So two different words there. So please make sure you get those differentiated. Number 15, relate temperature to evaporation. So when you talk about evaporation, the molecules have enough kinetic energy to evaporate, to move off into the gaseous form. So if you raise the temperature, now you're going to increase the evaporation. So the molecules that have enough kinetic energy can overcome the attractive forces and the atmospheric pressure and escape. So if you have a higher temperature, now you have a higher average kinetic energy, which means more is going to evaporate. Number 16, vapor pressure. So the vapor pressure is the force exerted by that gas, about a gas above the liquid. So if you have some alcohol, so say you have some ethyl alcohol in a container, you take that lid off. The minute you take that lid off, you can smell that it is ethyl alcohol. You can smell it. Rubbing alcohol that you have at home, you can smell that. Why? Because there's a lot of gas that's above that liquid. It has a high vapor pressure. So inside that container, it is evaporating and condensing, but when you open it up, it is released. So vapor pressure is the measure of the force exerted by that gas above the liquid. How does it measured? Well, it's measured is what's called a manometer, a manometer. So I have that term right here for us. Manometer. Vapor pressure is measured by a manometer. So apparatus with a U-tube filled with mercury that is taking the force of that vapor pressure and it moves. So when it moves, and they can measure the distance that it moves. So typically how it is you have a sealed container and you have a pipe coming like this. And you have mercury in that. And in here you have a liquid like that. And the vapor pressure is just sealed on the top. So the pressure builds inside here and it's gonna force that mercury up that elbow. And then they measure that distance that it goes up. That distance is the vapor pressure. So that's called a manometer. Number 17. Dynamic equilibrium in a closed system, and that's really important. Dynamic equilibrium is only in a closed system. So I have this container right here. It has a sealed lid, and I have this liquid in here. Dynamic equilibrium means that the rate of evaporation equals the rate of condensation. So we have some of the liquid evaporating and some of the gas condensing and going back into its liquid state. When that's all equal, there's no net change. It's in equilibrium. That's called a dynamic equilibrium. All right, number 18, vapor pressure and temperature change. So the higher the temperature of the liquid, the higher the vapor pressure. So if we come back up here to our manometer diagram that I just drew right here, if I increase the temperature on the bottom there that means the vapor pressure is going to build. That is why you never heat a stoppered flask or anything that's sealed. Why? Because now more and more of the gas is going to be able to escape into its gaseous form. It's going to build up pressure and will explode if it is not watched carefully. Number 19 is a repeat. It is vapor pressure is measured by a manometer and relate pressure to temperature. The higher the temperature, the higher the pressure. Number 20, what is boiling point? Boiling point is the temperature at which the vapor pressure of the liquid is just equal to the external pressure on the system. So, once again, you have this container right here, and in here you have a liquid. The reason that liquid is staying in that container is because you have pressure all around it forced down. When you have the temperature, so the vapor high enough that the vapor pressure equals the atmospheric pressure. So the atmospheric pressure is forcing down and the vapor pressure is forcing up. When those are just equal, that's when it boils. And the boiling is the little bubbles that come popping up out and going up, going into the gaseous state. That is the boiling point. The temperature when the vapor pressure of the liquid is equal to the external pressure on it, and now it'll boil. That's why those bubbles generate from within, coming up and out. Number 21, relate atmospheric pressure to boiling point. Relate atmospheric pressure to boiling point. The higher the atmospheric pressure, the higher the boiling point. The lower the atmospheric pressure, the lower the boiling point. So if you talk about a mountain, if you're at sea level right here and you go way up into a mountain here. So if you had water down at the bottom here at sea level, it's going to be 100 degrees Celsius. If you go up to the top of this mountain, less air pressure, now it's less atmospheric pressure. You might, at the top, you might, up here, you might be at something like maybe 90 degrees Celsius. So that is the relationship. Number 22, normal boiling point. That word right there is actually a definition, normal boiling point. That's the boiling point at sea level, which is 101.3 kilopascals. So 1 atmosphere or 101.3 kilopascals. That is normal boiling point. That's the temperature when the atmospheric pressure is 1 atmosphere or 101.3 kilopascals, and it boils. Whatever temperature that boils at, it's called a normal boiling point. Number 23, what is the melting and freezing point of a solid? And it says here, relate the specific temperature. So this is a concept. A little hard to think about sometimes. Well, let's define it. Melting point is a temperature when you go from a solid to a liquid. So it's in a solid state and it begins to go to a liquid state. That's melting. Freezing is when you go from liquid to solid, the temperature at which you go liquid to solid. It's the same temperature. That's why I have an equal sign there. It is the same temp. So when you talk about for water, 0 degrees Celsius is the melting and the freezing point, same temperature. It's in equilibrium. So at 0 degrees Celsius, 0 degrees Celsius, you have some melting and some freezing. So you're in equilibrium, going from the solid to the liquid, back to solid, and it's in equilibrium. Number 24. A crystal structure. That means, and you hear crystal, and we talked about this quite a bit in several chapters actually. Particles are arranged in a repeating pattern, an orderly repeating pattern. The unit cell, real important term, please make sure you get this term down. A unit cell, that's the smallest geometric shape that's repeating. So inside of a crystal, there's many different shapes of the crystals. But the smallest geometric shape that keeps repeating, that's called the unit cell. We have another term here, amorphous. Amorphous is a solid that lacks any internal organization. It's random. It is a solid, but it's not crystal. It is just put together. Concrete or macadam, those type of things are amorphous. They have no internal order. They're just random. And that's an amorphous solid. Glass. Glass has its own category. Transparent fusion produced by cooling to a rigid state without forming a crystal. Another word for glass is a supercooled liquid, a supercooled liquid. So you heat silicon dioxide, which is what glass is made out of. You heat that very hot, and it makes this transparent fusion, and it doesn't form a crystal, but it's transparent. So therefore, when you heat it, it sort of melts, and that's what glass does. So it becomes flexible and that. So glass is a transparent fusion produced by cooling to a rigid state without a crystalline structure. It's also known as a supercooled liquid. Number 25. What is an allotrope? An allotrope, that's a new term for us, an allotrope. Please make sure you get that and write that term down, an allotrope. And some examples. So an allotrope is two or more forms of the same element. Two or more forms of the same element in the same physical state. So please make sure you get that. An allotrope is two or more molecular forms of the same element in the same physical state. It's not a lot of elements have allotropes. Carbon has 3 allotropes. You need to know that. Carbon is the example of an allotrope I want you to know. Carbon has a diamond structure. That is this repeating geometric shape that's within. It's a crystal structure, so you're familiar with what a diamond looks like. Then you have graphite. Graphite is typically what your pencil lead is. Graphite is layered. It's soft and layers of hexagonal arrays. So there's just these sheets, these layers of sheets that are bonded together, but they're soft. It's still carbon. It's just an allotrope of it. So you have a crystal diamond structure, then you have this sheets. That's graphite. Lastly, you have fullerenes. Buckminster fullerenes or buckyballs, those are said to be the hardest known substance. There are 60 carbons in this spherical shape, 60 carbons in this spherical shape, and those are fullerenes. So, allotropes of carbon is diamond, graphite, fullerenes. Please know those 3. Number 26, differentiate between the melting point of ionic solids and covalent solids. In general, because a diamond is a covalent carbon and it is extremely high. In general, the melting point of ionic compounds is very high and covalents are typically low. That's a general rule. Number 27, changes of state. That's a phase diagram. That was our last lesson that we had. Phase diagram. It's a graph that gives the condition of temperature and pressure at which a substance exists as solid, liquid, and gas. Lines on the phase diagram represent the equilibrium of 2 phases. So we talked about this. You have the Y and you have the X. Typically, this is your pressure, and here is your temperature in Celsius. You have a line coming up like this. You have another line coming down typically like that. Here you have solid, liquid, and gas. The line on a phase diagram, huge importance. Line on a phase diagram represents equilibrium between those 2 phases. 28, sublimation. Change of a substance directly from solid to gas. So it doesn't go into the liquid state at normal temperature and pressure. It just goes from solid to gas. That's sublimation. Example for sublimation was dry ice, which is solid carbon dioxide, and iodine. Deposition, our next term right here, that is going from the gas directly back to the solid state. And examples, I already mentioned those two examples. Please know those two examples as sublimation and deposition. Number 29, what is the triple point? And that is this point right here on this little graph I drew, the triple point. It describes the only set of conditions at which all three phases exist in equilibrium. So if you have the triple point, say for water, for example, you say the triple point of water. So at the triple point, which is right above freezing and just above a vacuum, it is boiling, it is condensing, and it is freezing, all at the same temperature. And that's the beauty of triple point. That's what that means. Number 30 and last one is please be able to understand if you were shown a phase diagram, knowing what those lines mean, what the triple point means, and what the axes are. So the y-axis is pressure and the x-axis is temperature. So ladies and gentlemen, that is it on your study guide. Hopefully you took some good notes on this. Please go through this very carefully, look through the notes you took from the virtual lessons. And we have a quiz on Thursday morning. It'll be on Moodle and it is timed. It's 7 questions and you have 15 minutes to do those 7 questions. It'll give you a little practice on using Moodle for assessment. And then Monday, we'll have our Chapter 13 Moodle test. It'll be worth 50 points. Thank you for watching. Go in peace.